Day 18 of 60. Today we are covering rate limiting algorithms. Every production API needs rate limiting, but the algorithm you pick determines whether your system degrades gracefully under load or falls over. We are going to walk through 5 algorithms, implement them in Python, and I will tell you which one to use for each scenario. Let us start with the token bucket algorithm. This is the most widely deployed rate-limiting algorithm in production. The concept is straightforward. You have a bucket that holds tokens up to a maximum capacity. Each incoming request consumes 1 token. Tokens refill at a fixed rate over time. When the bucket is empty, requests get rejected with a 429 status code. The key advantage here is burst tolerance. If a client has not sent requests for a while, the bucket fills up and they can send a burst up to the bucket capacity. Then they settle back to the refill rate. This matches how real API clients behave. They send a batch of requests, wait, then send another batch. AWS API Gateway, Stripe, and most CDN providers use Token Bucket internally. The implementation uses a lock for thread safety, tracks the last refill time, and calculates how many tokens to add based on elapsed time. In production, you would store this state in Redis instead of local memory so the limit applies across all your application instances. Next is the Leaky bucket. Leaky bucket flips the model. Instead of consuming tokens, requests enter a queue. That queue drains at a fixed rate regardless of how fast requests come in. If the queue is full, new requests are dropped. The output is perfectly smooth, which is valuable when your downstream dependency has strict throughput limits. Think outbound webhook delivery or background job processing where you need consistent pacing. The trade-off is zero burst tolerance. Even legitimate traffic spikes get queued or dropped. You would not use this for a user-facing API where responsiveness matters, but it is exactly right for systems that need to pace their output. Now the fixed window counter. This is the simplest approach. Divide time into fixed intervals, say 60-second windows. Count requests per window. If the count exceeds the limit, reject. In Redis, this is just an INCR on a key that includes the window number and an expire for cleanup. Dead simple, memory efficient, and it works. But there is a well-known boundary problem. Imagine a limit of 100 requests per minute. A client sends 100 requests at second 59 of one window, then 100 more at second 0 of the next window. They just sent 200 requests in 2 seconds while staying within the per-window limit. For login throttling where the limit is 5 attempts per 15 minutes, this boundary issue is negligible. For DDoS mitigation, it is a real problem. That brings us to sliding window solutions. Sliding window log solves the boundary problem by keeping a sorted set of timestamps for each request. When checking the limit, you remove entries older than the window duration and count what remains. No boundary issues at all. But memory scales linearly with request volume. At 10,000 requests per second, you are storing 600,000 timestamps per client per minute in Redis. That is fine for low-volume, high-value endpoints like authentication or payment processing. It is not practical for high-throughput API endpoints. The sliding window counter is the production sweet spot. It keeps counters for the current and previous fixed window, then weights the previous window count by the fraction of overlap. If you are 40% into the current window, the previous window contributes 60% of its count. Memory stays 1 per client, same as fixed window, but you eliminate most of the boundary problem. This is the algorithm I default to for most production rate limiting. Let me give you the practical cheat sheet for choosing an algorithm. For API rate limiting, use token bucket or sliding window counter. Burst tolerance keeps user experience smooth while enforcing fair usage. For login throttling, fixed window is fine. The boundary problem is negligible when limits are 5 attempts per 15 minutes. For DDoS mitigation, sliding window counter at the edge. No boundary exploitation and low memory overhead per source IP. For webhook delivery or outbound API calls, leaky bucket. Downstream services need consistent pacing, not bursts. Whatever algorithm you choose, always return rate limit headers. X rate limit tells the client their quota. X rate limit remaining tells them how much is left. X rate limit reset tells them when the window resets. And when you reject a request, return a 429 too many requests with a retry after header. Clients that self-regulate based on these headers reduce load on your infrastructure without you having to do anything. That is day 18. Tomorrow we will look at how rate limiting integrates with load balancers and API gateways at the infrastructure layer. See you on day 19.